Good afternoon, class. We are looking at Chapter 2, Limits, Section 2.4, Limits, Algebraic Method. 2.5, Continuity. We covered limits of sequences, limits of functions at infinity, limits of functions at finite numbers, and now we're going to look at algebraic methods and continuity, reminding you, everybody, of the definition of a limit. The limit exists if one-sided limits are identical. That means the limit of f of x as x approaches a from the left is L, the limit of f of x as x approaches a from the right is L, therefore the limit exists. So in summary, a sequence is an ordered list of numbers or functions f whose domain is the set of natural numbers. Limit refers to the long-term behavior of a sequence, i.e. what happens to a sub n of a sequence in the long run. The limit of a sub n as n approaches infinity is L. We say that a sub n converges to L. If this limit is either infinity, negative infinity, or DNE does not exist, then we say it diverges. And in short, we just plug in and we observe. There are some theorems we discussed. The limit of 1 over n to the power of p as n approaches infinity is 0. For p larger than 0, and the limit of r to the power of n as n approaches infinity depends on the base. If the base is between -1 and 1, not just 0 and 1 is 0. If it's 1, it's 1, and if it's larger than 1, it's infinity. So the geometric sequence, when we add them up, becomes a geometric series, and the sum is a times 1 minus r to the power of n over 1 minus r. And when r is between -1 and 1, this piece goes to 0, we get a over 1 minus r. The recursive solution b sub n plus 1 is r b sub n, and the explicit solution is b sub 0 r to the power of n or a r to the power of n. In the case of medication, for example, when we give medication to patients at a time step with a constant of c, and what remains in the body is r, the portion, if you will, then we get this formula where b sub n is b sub 0 r to the power of n plus c times 1 minus r to the power of n over 1 minus r. And also we looked at HA, horizontal asymptotes. Horizontal asymptotes, by definition, for the function y equals f of x, is the line y equals n. If the limit of f of x as x approaches negative infinity is L, or the limit of f of x as x approaches positive infinity is L, in either case. Now, reminding you of the VA, vertical asymptote. If the limit of f of x when x approaches a, or a from the left or a from the right, is either negative or positive infinity, then we have the VA, vertical asymptote, with the equation x equals a. And I want you to pay attention to all of these graphs to really, again, to remind everybody, to really understand the concept of a limit from a graphical point of view. Here's a along the x-axis. When we approach a from the left or right, left or right, left or right, in all cases, from the bottom and from the top, it approaches L in all cases. So the limit exists for all cases. The limit of f of x as x approaches a is L. The difference is, in this case, f of a is also L because we don't have a break, we don't have a hole, and precisely at a. Whereas here, precisely at A, the solid point gives us B. Precisely at A, we don't have a solid point, the limit. The functional value is missing, is undefined. So I hope everybody is comfortable with this concept. Now, let's go to the idea of a limit laws and remind everybody of what we have learned. If the limit of f of x as x approaches a and the limit of g of x as x approaches a, if these two exist, Then limit law says you can use for example, the main four operations. The limit of the sum is the sum of the limits. We have discussed this before. The limit of the difference of the limits. The fourth one, the limits of the product is the product of the limits, and the limit of the quotient or the ratio is the ratio of the limits. Needless to say, the denominator can't be zero. Number 3 says if you have a constant, you can take it out because the limit pertains to x. Direct substitution property. A continuous function at a has the following limit value. The limit of f of x as x approaches a is equal f of a. Is the functional if the functional value, that means precisely at a, is equal to the limit value in the vicinity of a, then the function is continuous at a, and functions with the direct substitution property are called continuous at a. A warm-up example using limit properties or limit laws. So you cut this into 1, 2, 3 pieces according to the limit laws. This one is the limit of x as x approaches 4 to the power of 2. This one, the negative 3 sits in front because it's a multiplier. According to limit laws, now you can replace the x with 4, okay? Now you can replace the x with 4. The last one, when you have a constant, x approaching 4 or 40 or 10,000 or 2 or negative 5 has no bearing, the constant comes out as a constant. And 4 squared minus 3 times 4 plus 7, this is 16. Minus 12 is 4. Plus 7 is 11. Or we could simply plug in as we did before. Let's look at the graph and see what we can do. And I want to remind you that you have the PowerPoints and it's easier to follow, okay, from the PowerPoints that is given to you, because it's hard to draw this and not miss anything. So the very first step is to use the limit laws and write the limit of this one plus 5 times the limit of this one as x approaches negative 2. So that's the first thing, very straightforward. From the graph, we are going to find this one. And by the way, the red function is the f function, the blue function is the g function. Can anybody tell us what is the limit of f of x as x approaches negative 2? Is number negative 2. Approaching from the left side of negative 2, we are moving towards this point. And this one has y coordinate 1. From the right side of negative 2, we are moving this way, right side of negative 2, and we are moving towards the same point, having the same y coordinate, namely 1. Therefore, the limit of f of x as x approaches negative 2 is 1. As far as the g function is concerned, here's from the left of negative 2, here's from the right. In both cases, from the left and right, we are moving towards the same point. Now, this point has a y coordinate negative 1. Therefore, this is 1 plus 5 times negative 1, which is negative. The limit of f of x times g of x as x approaches 1. Again, let's separate them into two pieces. The limit of f of x as x approaches 1 times the limit of g of x as x approaches 1. Can anybody tell me what's the limit of f of x as x approaches 1? Here's number 1 on the x-axis. From the left side, we are going this way. We are in this branch, and it's moving towards this point, and it has a y coordinate, positive 2. From the right side of number 1, we're going this way. And as you go this way, that means you're in this branch, and we are moving towards the same point having the same y coordinate, namely 2. For the g of x, what is the limit of g of x as x approaches 1? From the left side, so this doesn't exist. This doesn't exist. Why is that? Because here's the left side, everybody. We are moving in this direction towards this hole, and that has a y coordinate negative 2, but from the right side, we are here moving towards this hole. By the way, we never get to those points, okay? We get very close to them, and with that, this one has a different y coordinate, namely negative 1. So the limit of g of x as x approaches 1 from the left is negative 2, which is not equal to the limit of g of x as x approaches 1 from the right, which is negative 1. Because this is the case, this limit doesn't exist. And the product of 2 and does not exist does not exist. So the limit here does not exist. We can have a different approach, and I'm going to quickly show you. The second method is to find this as x approaches 1 from the left and as x approaches 1 from the right. Starting from the left, for this function, left and right makes no difference, is 2. For this function, the left means minus 2. So 2 times minus 2 makes it negative 4. From the right, and that's not equal from the right. The right, for this function, again, it doesn't change, but this function, it changes to negative 1. The product of 2 and negative 1 is minus 2. These two numbers are different. Therefore, the limit of f of x times g of x as x approaches 1 does not exist. Now, I want to discuss the solid point. So f of negative 2, that refers to the precise location when x is negative 2. The precise location is here. And what is the y coordinate for this point? Is 2. For g of 1, we are looking at this point, the solid point, and the y coordinate is negative 2. So again, this one, the dot, the solid dot, the solid point has the y coordinate negative 2. So what you notice, the limit of g of x as x approaches 1 doesn't exist. But when you look at these two numbers, one of them is negative 2, one of them is negative 1. The one which is negative 2 is identical to g of 1. Later on, we discuss this means the function is continuous. First of all, the function is discontinuous at this point anyways, okay? By this function, I mean g at x equals 1. But we say it's continuous from the left because it has a solid point. This function, the limit of absolute value of x over x as x approaches 0, dne does not exist, and we want to see why, and I'm going to remind you of the one-sided limit. First and foremost, here's the graph. Let's discuss the reasoning behind that. First, remember the absolute value of x by definition is x when x is larger than or equal to 0 and negative x if x is less than 0. With that being the case for this function, if we call it f of x or y, and you replace the same thing, it becomes, for the top, becomes x over x, which is 1. For the bottom becomes minus x over x, which is negative 1. However, this has the equality here, but none of them have the equality because x is in the denominator, so we don't have the equality. So this is equal to 1, that means a half line, and of course the endpoint is not included. Half line y equals 1. This is the half line y equals 1. This is the half line y equals negative 1. And both of them have holes here. Now, the limit of this function as x approaches 0 from the left, so we are moving towards this point, which has the coordinate, the y coordinate negative 1. But from the right side, we are moving towards here, which has a y coordinate positive 1. Are they identical? The answer is no. Therefore, the limit of this function as absolute value of x over x as x approaches 0 does not exist. Now, as you remember, when we are dealing with limits, we basically are going to plug in. So can you quickly plug in and give me the answer for part A, class? When you plug in, what do you get? Anybody has the answer?
3 over 2.
Perfect. So 2 squared is 4, times 2 is 8, and 1 is 9. 3 times 2, 6 minus 2 is 4. So square root of 9 over 4, which makes it 3 halves. Perfect, meaning it just works out. We are done. For part B, if I plug in negative 4 to the top and to the bottom, what do you think I get? You get 0 over 0. Please remember, 0 over 0 is not undefined, it's not 0. It's indeterminate. And if you recall, I said to me, indeterminate means more work. What does it mean, more work? Algebraic techniques. And we've been exposed to some algebraic techniques, so we need to know what algebraic technique we need here. This is a complex fraction. The basic definition of a complex fraction is a fraction within a fraction. The technique for a complex fraction is LCD, the least common denominator. You have one fraction here, 1/4. You have the second fraction here, 1 over x. and 4x is the LCD. I'm going to multiply by 4x and divide by 4x. It's important to understand that you can't just say I'm going to multiply by 4x because this has to be 1. Now, notice when we have 0 over 0, it is the 0 in the denominator which gives us a hard time. So it is the 0 in the denominator we want to get rid of. It is x plus 4 that we want to get rid of. Therefore, as far as the bottom is concerned, we don't do anything. We just write them as a product, okay? The top, if you multiply 1/4 and 4x, 4 goes away, you get x. If you multiply these two, x goes away and you get 4. And now, x plus 4 cancels out. We get 1 in the numerator. Remember, we carry the limit sign from a to z. Now that I'm going to replace the x with -4, I can lose it and write -1 over 60. So in this case, complex fraction required the algebraic technique of using LCD, the least common denominator. Part C. Can anybody tell me what we get if we plug in? Zero over zero, it's indeterminate. And because it's a rational function, the technique is factoring. So your factoring techniques must be good. One thing that I want to add that will help you with the factoring. Remember, it is the 0 in the denominator that we should get rid of, okay? That's the one that is bothering us. Because x is approaching 4, we must have a factor of x. Because x is approaching 5, we must have a factor of x minus 5. If it's approaching 10, x minus 10. If it's approaching 2, x minus 2. What if it's approaching a negative number? For example, -10, we should have a factor of x plus 10. In the numerator, we notice this is minus 5 squared. So we use a minus b times a plus b is a squared minus b squared. The factoring will give us a chance to get rid of x minus 5. And notice the denominator does have a factor of x minus 5. This is what we end up with. If we plug in 5, we get 10 over 5, which is 2. Part A, what do you think we get if we plug in? Anybody? Can you guess what we get if we plug in? Zero over zero. Since x is approaching 4, we should have a factor of 4. And I'm going to remind you of this factoring technique. So we need to do factoring, okay, because we are dealing with rational expression. We want two numbers. The product is c minus 4. The sum is b minus 3. The top is very simple. Just take the x out. This becomes x minus 4 over x plus 1. Again, I'm hoping everybody is comfortable with factoring. We cancel out the common factor of x minus 4. And if we plug in 4, we end up with 4 over 5 as the final answer. What do we get in part B when we plug in? Anyone? If we plug in, what do we get? Zero over zero, which is indeterminate. Anybody remembers the technique we mentioned for this case? Anytime we have a square root, the technique is what? Using conjugate. The conjugate of A minus B is A plus B. Their product is A squared minus B squared. Therefore, all you have to do, change this one to a plus sign. However, when you do that, you have to put it at the top and the bottom both, because this expression must be equal to 1. Otherwise, you can't do that. Remember that the problem is h because it's approaching 0. And the technique is, for the denominator, you don't do anything. You don't distribute, you just keep it as a product. For the numerator, you get the square root of 1 plus h quantity squared minus 1 squared, and that gives you 1 plus h minus 1 in the numerator. As I said, the denominator, you don't touch it. One thing I want to remind everybody is that if you have minus 1 squared, by the order of operation, this is negative 1, because first you square number 1 and then times negative 1. Please don't mix them up. These two are two different things. This is positive 1. And so 1 and negative 1 cancel each other. The h at the top and the bottom cancel each other, giving us 1 in the numerator. If I replace the h with 0 here, square root of 1 becomes 1, with 1 becomes 2. So 1/2 is the final answer, everybody. Okay. Same thing here, we plug in. And again, sometimes it works, sometimes it doesn't. Can anybody tell me what we get when we plug in? What do we get when we plug in x equals negative 4? Anyone? Okay, nobody knows? Or nobody wants to participate? We get 0 over 0. We're going to multiply by the conjugate of the numerator. That means we change the negative to positive. You multiply and divide by it. This expression must be 1. And as I mentioned, you multiply the bottoms without distributing, you just leave it alone. Why is that? Because x is approaching -4, makes this one 0, and a factor of x plus 4 is a problem we are hoping to get rid of. So what happens to the top? We are multiplying these two, we get a squared, which means the square root of x squared plus 9 squared minus b squared minus 5 squared, which gives us x squared plus 9 minus 25, or x squared minus 60. This is 4 squared. So we have x minus 4 and x plus 4. See, we were hoping to get rid of this factor, and now we could. And that's really the idea behind multiplication by the conjugate. This is what you want to achieve, and we did that. Now, if you plug in, the top is -4 minus 4. The bottom is over here. When I put -4 squared, it becomes 16. 16 and 9 is 25. And the square root of that, this thing is 5. So this thing is -8 over 10, which simplifies to -4 over 5. A fraction must always be put into its lowest term, always. Any questions, class? Again, all of these that are being recorded, it's a good practice to go over them a couple of times to be on the safe side. All right, part A, I want everybody to work on that. Part A, plug in first. Put it on your paper, plug in, plug in. What do you get, class, when you plug in? Evaluate it at x equals 6, plug in, what do you get?
0/0.
No, that's not what we get. Plug in, evaluate it. Don't guess. Work it out. Anyone? What's the answer? Nobody knows that? Can you evaluate this expression by replacing x with 6? Anybody has the answer? If you plug in 6 here, this is 0 and this is 3. This one is 36 minus 42 plus 12. 36 minus 42 plus 12 is 6. 3 over 6 is 1/2. So it's not always 0/0. Evaluate it. This is very basic, class. Just plug in. And you plug in, you get 0/0. This is a complex fraction. The technique is LCD, which is 3x, and we multiply and divide by. This one, we write it as a product. This one, 1/3 times 3x gives us x. 3x times 1 over x gives us 3. So we keep the sign. And x minus 3 cancels out x minus 3. Notice the lim sign doesn't go away until now that we are going to replace the x and we get 1 over 9. Any questions, class? Again, in short, plug in. If it gives you any number, you're done. If it gives you indeterminate form, such as 0 over 0, infinity over infinity, infinity minus infinity, you have to use your techniques. By the way, there are other forms of indeterminate, such as 1 to the power of infinity, infinity to the power of 0, things of that nature, okay? There are more, but we are limited to a few. Continuity. A function f is continuous at x equals a if this is true. The limit of f of x as x approaching a equals f of a. If the limit and functional value are identical or equal, the function is continuous. Therefore, we have to look at the following situation. Number one, f of x exists. The output at a exists. Number two, and that means the functional value. Number two, the limit of f of x as x approaches a is L. That exists. That means the limit as x approaches a. That means the one-sided limits are identical. Finally, this limit, this is part two, is equal to this functional value f of a. So the limit is the same as the output. So a function is continuous over an interval I if it is, so that's for a point A. A function is continuous over an interval I if it's continuous at each point A in that interval I. If f is not continuous at x equals a, we say that f is discontinuous or has discontinuity at x equals a. For example, this graph. This graph is given at which numbers is f discontinuous and why is that? Well, clearly at 1. Why is that? Because does the limit exist? Yes, because both sides, they go to this point, whatever this value is. But what is f of 1? I'm looking for a solid point. I don't find it. F of 1 is not given, is not defined. The next one is number 3. Why is that? A lot of reasons, okay? But the main one is that the limit doesn't exist. From the left side, we go here, and whatever this number is, the limit of f of x as x approaches 3 is this number. From the right, we go here is this number. So the limit of f of x as x approaches number 3 does not exist. DNE does not exist. Also, at 5, so what happens at 5? We want to see what's the difference between 5 and 1. Again, we have a discontinuity, but the difference is the limit exists just like before. Over here, the limit exists too. Over here, what is f of 1 is not given. Over here, what is f of 5 is given, the y coordinate for this point. But are they identical? No. So the limit of f of x as x approaches 5, this is given, but they must be identical. They are not, therefore the function is discontinuous at that point. So we don't know f of 1. The limit doesn't exist. The limit exists. We know f of 5, but they are not identical. What about this function? It is a piecewise defined function. G of x is defined as half of x plus 3 for x less than -2 and x minus 1 for x larger than or equal to -2. And we want to see whether the function is continuous at x equals -2. Why are we looking at the endpoint? I want you to notice that the top one is a linear function. A linear function is continuous everywhere from negative to positive infinity. The bottom one is linear, also continuous from negative to positive infinity. Therefore, this is continuous from negative infinity to -2. This is continuous from -2 to infinity, except we have to check at specifically -2 to see what happens. So first, there are three things we want to look at. When we look at this one, we want to look at the functional value and we want to look at the limit. So the functional value, it means we want exactly the function at x equals -2, and we are concerned with the equality. To find the function value at this point, we look at these two. The one that has the equality, that's the part we are going to use. So g of -2. Here's a notation. We use this part such that this line segment is read such that x is -2. What this means, it means evaluate this function when x is -2. So -2 minus 1 makes it -3. So at x equals -2, g of x is -3. So g of -2 is -3. For the limit, we are going to look at one-sided limit. That means limit from the left, limit from the right. So if I'm looking at limit from the left, that means x less than -2, I have to look at this branch. So if I plug in -2 here, class, with 2 cancel each other, we get -1 and 3. It's 2. So the limit of g of x as x approaches -2 from the left uses this branch because this is less than. We evaluate it, we end up with 2. We're going to do the same thing, but this time -2 from the right. -2 from the right, that means larger than -2. That means this branch, we are going to use this one. So that was the left-sided. Now this is the right-sided. And we use this piece. If you plug in -2, -2, and -1, they add up to -3. Now, obviously, the limit from the left and the right of -2 are not identical. The limit does not exist, which means the function is discontinuous at x equals -2, or it's not continuous. One thing I want you to observe is that the functional value is -3, and the limit from the right is also -3. Again, it doesn't change the fact that the limit doesn't exist. It doesn't change the fact the function is discontinuous at x equals -2, or it's not continuous. But sometimes it's important to calculus to know it means g of x is continuous at x equals -2 from the right. So which means if you graph it, this piece, the right piece, have a solid point at the end. That's the meaning of it. Let's discuss also types of discontinuity. When we look at this function versus this function, okay, parts A and C, those are considered removable discontinuities. We could remove the discontinuity by redefining f at just the single number 2. Just one number. Over here, I have to redefine f of 2. The same thing here. See, f of 2 here seems to be 1. And maybe we need 3 here. So the limit and the functional value must be the same. In order to remove the discontinuity, this has to move up there, meaning the limit must be equal to the functional value. So you redefine this. So that's the problem here. Whereas here, we don't even have that. Now notice this one, if I do the factoring x minus 2, x plus 1 over x minus 2, they cancel each other. This becomes x plus 1 when x is not equal to 2. Please understand, this function, g of x equals x plus 1, which has no restrictions, is a linear function, is continuous everywhere. But this function is continuous everywhere except at x equals 2. And the only way to fix it, to remove the discontinuity, is by redefining f of 2. However, if you look at this case, no matter what you do, whether this is defined or not, there is nothing we can do to fix. This is infinite discontinuity. This one is a step function, right? You see the steps. There is nothing we can do to fix these two. This is the infinite discontinuity. This one is a jump discontinuities. These two, there is no way to fix them, but this one is called removable because by redefining the function at a singular point, we can fix the discontinuity. Is h of x continuous at x equals 3? And h of x is defined as x squared minus 9 over x minus 3 for x not equal to 3. And it's 7 for x equals 3. By the way, please understand, because this function has a denominator, the domain is all real numbers except x equals 3. And that's why it makes it discontinuous at that point, okay? And if you can, if the top is divisible by the bottom, it becomes just a whole. But if it's not, it becomes at x equals 3 becomes a vertical asymptote. So we are going to look at the limit as x approaches 3. And to do so, we notice if we plug in, you get 0 over 0. And the technique is factoring. We've discussed that all along. It's a rational expression. The technique is factoring. The top is x plus 3, x minus 3 in any order. So it's the limit of x plus 3 as x approaches 3, which makes it 6. So the limit exists for the function, and it's 6. However, what is given? What is the meaning of this? The meaning of this h of 3 is 7. That's the meaning of it, class. This means this, okay? H of 3 is 7 according to this. Is this equal to the limit? No. Therefore, h of x is discontinuous at x equals 3. In order for a function to be continuous at any point, the limit of f of x as x approaches a must be f of a, and or in this case, h of a. So h of 3 is not equal to the limit of h of x as x approaches 3, therefore discontinuous at x equals 3.